Right, very good afternoon. Today, let's discuss the new topic. This ARIMA or the ARMA model. Uh, so then, why we are using the ARMR or the ARMA or the ARIMA model? Most often, our goal is, our objective after collecting the data, our objective is to find the statistical model to describe the real-time series data series, and then using this time series data or the using this estimation, we want to predict the future, that is forecasting, estimation and forecasting. The one there are many models to describe the estimate, how we use the our model estimation for future forecasting. There are many models. Popular model is ARMA model, ARMA model. Using ARMA, AR means auto regression, MA means moving average. Combination of these two we call the ARMA model. The ARMR or the ARMA model is used. So then why we are using ARMA models? For predicting the future. Using ARMA model to describe the real-time series, we called Box-Jenkins methodology. Using ARMA model to describe real-time series is called Box-Jenkins methodology. ARMA model cannot be applied to any time series. Any time series we cannot apply. The ideal series, our series should be stationary. We discuss what is stationary is. If your time series data are stationary, then you can use ARMA model. ARMA model is used to predict the future. Using ARMA model to describe real-time series, we call this Box-Jenkins methodology. Then what is, again, when reminding you why stationarity? Stationary is nice property, or it is very good characteristics of the time series data. Suppose, for simply saying, assume that we have two sample data for the time series, two sample data. One sample is year 1981 to the 1990. Another sample 1991 to 2000. If the series is stationary, then the two samples should give approximately the same estimate for mean. Mean in terms of mean, in terms of variance, in terms of covariance. Two sample estimates should be approximately same. Those since those moments do not depend on the understationarity, then we call that no stationary. But if the two samples produce significantly different estimates, assume that mean of 1981 and 1990 and mean of 1991 and 2000. During that period and during the period of 1981 and 1990, the mean difference, if you can see the mean difference between these two periods, then we called our data series are non-stationary, right? It is, in terms of mean, we can see the difference. In terms of variance or covariance. Then the two sample produce significantly different estimates. Then the series is likely to have structural breaks and the non-stationary. So then structural break to a series has a structural breaks, and then we call data are non-stationary. Then using history to forecast future. Then how to forecast if two sample in the same analysis, but the sample is different, their data range is different. If the data duration is different, estimations are different, then we cannot forecast for the future. History, we use the history, that means past value. For the estimation of the past value, using the past value, we forecast the future. The future forecast using history for future forecasting cannot be justified until stationarity holds. That's why we convert the data to the stationary process. Using non-stationary data, we can't use for analysis. Then time series data process. If you have, that most of the accounting, most of the finance, economics data are time series. When the time series data, if it is time series, the data set are non-stationary. Then the data, how to analyze the time series data. What we need to do is we need to prepare our data set. How to prepare our data set? Plot the data and examine for the stationarity. Plot the data first. If you have a time series data set, plot this data set and examine whether data series are stationary or not. Also, plot for stationarity can be checked by using plots. Plotting the data. Also, the stationarity can be checked by using ACF, autocorrelation function. ACF means autocorrelation function. Assume that data series are not stationary. Then take the first difference. If variance appears non-constant, the variance appears, it's non-constant, take logarithms before first difference. Then examine ACF after these transformation of data to determine if the series is now stationary. Right, this is the first task you need to do if your data series are time series. What you need to do is first check the stationarity by plotting the data, or examine the autocorrelation function. If the data are not stationary, then take the first difference. If the variance appears non-constant, then take the first logarithms before differencing. After differencing, then consider the first after transforming the logarithms, then convert these data to the logarithm first, then take first difference, then check ACF then check the stationarity. The model identification. The next step is model identification and estimation. Examine the autocorrelation function and partial autocorrelation function of your stationary series to get some idea about the ARIMA model to estimate. Right, after doing the stationarity, then examine the ACF and partial autocorrelation function. ACF means autocorrelation function. PACF means partial autocorrelation function of your stationary series to get the ARIMA model. ARIMA model is used to estimate and forecasting purpose. Then estimate the ARIMA models. Then examine the parameter estimates by using SPC statistics and test of white noise for the residuals. Then this is the model identification of the ARIMA model. Then go for the forecasting. Then use the base model to construct the forecast. Then graph your forecast against your actual values and calculate the mean squared errors for the forecast. Those are the steps we need to follow. Right. So then let's discuss the univariate ARIMA model. You know that in regression analysis, if the error term in the regression analysis, you know there is an error term. It is autocorrelated. Error terms are not independent. It is not independent. It is autocorrelated. The efficiency of ordinary least square parameters estimates get adversely affected and the standard error estimates are biased. The autoregressive integrated moving average. What is ARIMA means? Autoregressive integrated moving average. ARIMA model is fit for data with uncorrelated errors. Data with autocorrelated errors. This happens frequently with time series data. If the data error term is not correlated or autocorrelated, our errors are autocorrelated, then autoregressive moving average model is used. Then ARIMA procedure analysis and forecast equally spaced univariate time series data, transfer functional data and intervention data using the autoregressive moving average model or more general autoregressive integrated moving average model. ARIMA model predict a value in response time series as a linear combination of its own past values, past errors, and current and past values and other time series. An ARIMA model, autoregressive integrated moving average, ARIMA model, contains three different kind of parameters. The P, this is we call autoregressive parameters. Q, Q means moving average parameters. And the variance of the error term. Then the amount of total. P means, what is P here? Autoregressive parameters. Q means moving average parameters. And the variance of the error term. These parameters are always estimated by using the stationary time series. A time series is stationary with respect to its mean and its variance. Let's discuss the using autoregressive model. Here we say that using ARIMA model to describe time series, using ARIMA model to describe the real time series, we call it Box-Jenkins methodology. We use Box-Jenkins methodology. It's a Box-Jenkins methodology. What is Box-Jenkins models? Then today we discuss what is the Box-Jenkins model, what is forecasting with autoregressive model, that means AR model, forecasting with moving average models, MA model, autoregressive integrated moving average model, ARIMA model, trends and seasonality in time series, what is trends and what is seasonal data, and the summary. Univariate data. Univariate data may be stationary, maybe it include trend, maybe the series are seasonality, maybe the series are cyclical. Majority of the real world data shows certain combination of these patterns: stationary pattern, trend pattern, seasonality pattern, and cyclical pattern. For example, first, after gathering the data, first plot the data. The plot of the raw data indicate non-stationary. Although there does not appear to be a strong trend you cannot see, but its data series are non-stationary, it doesn't have not zero mean and variance. Then plot and then see the autocorrelation function. Autocorrelation function plot is produced This plot, autocorrelation function, already clearly indicate a non-stationary series. That means the autocorrelation diminish only. It diminish, you can see it, autocorrelation, it diminish very slowly. This autocorrelation plot, you can see that it decrease, autocorrelation plot, this plot decrease, it indicate a non-stationary series. Then we convert the data to the first difference. If we convert the data to the first difference, then this is the behavior of the data, graphical illustration, and this is the partial autocorrelation. So this is the autocorrelation graph. The ACF, then now you can see the ACF shows the autocorrelation diminish fairly quickly. So we decide that the first difference of the capacity utilization rate is stationary. The first difference is of the capacity utilization rate is ACF. This graph shows the autocorrelation diminishes very quickly, fairly quickly, comparing to the previous one, diminishes very slowly, this diminishing quickly. Then we decide this, diminish quickly, this diminish very slowly, this diminish very quickly. Then so we decide the first difference of the capacity, the variable is stationary. In addition, this is the first job we need to do, plot the data to check the stationary, then examine the ACF for stationary. If the ACF diminish very slowly, it includes, that's the indication for the autocorrelation. If the ACF diminish very quickly, it is the data series are stationary. The first difference, if not stationary, take the first difference and then check the same. Now next step is, in addition to the autocorrelation function and partial autocorrelation function, in eViews, there is a check for white noise. In other softwares, we have another softwares instead of eViews. There is a software package called SAS. SAS means SAS, or the starter. It shows the white noise check. It print out the junk box statistics called chi-square below the probability values. If the probability value is very small, as they are below, then we can, probability values are very small. Here, probability value are very small. Here 0.0011, very small. Then we reject the hypothesis. Autocorrelation up to the stated lag are jointly 0. For example, for our capacity utilization data, first difference, this is the data series is white noise. At least one is non-zero. Chi-square value is 136. 0.45 with the probability value is 0.001, then we reject our H naught, then we accept at least one is non-zero. Then the series is not white noise. A check for white noise on your stationary series is important, because if your series is white noise, there is nothing to model and thus no point to carry out any estimation or forecasting. If this is very important, if your series is white noise, there is nothing to model and no point to carry out for forecasting. We see here that first difference of capacity utilization is not white noise. It is not white noise because we accept this. So then we can proceed the model for estimation. Right here, very important, we can ignore the autocorrelation check for the data before differencing, because it is before differencing it is non-stationary. Then the model identification and estimation. Our next after that, after data preparation, right? This is the data preparation task. Then model estimation and other model identification. Examine the autocorrelation function and partial autocorrelation function of your stationary series to get some idea about what ARIMA model to estimate. What ARIMA model we estimate. For that, we need to examine the autocorrelation function and partial autocorrelation function. Why we are checking the autocorrelation function and partial autocorrelation function? To get some idea about the ARIMA model. Here in ARIMA model, we are writing like this: P, D and Q. What is P means? D means ARIMA model stand for the number of time data have been differencing. D means differencing in order to make the series stationary. This was already determined in the previous lectures. D means difference. P means autoregressive component. To get the idea of what order to consider. For that, we need to examine the partial autocorrelation function. If the series has an autoregressive order of 1, we call AR1. Then we should see only the first partial autocorrelation coefficient is as significant. If it has a AR2, then we see only the first and second partial correlation coefficients as significant. They could be positive or negative. What matters is the statistical significance. The partial autocorrelation function will have significant correlation up to the lag P and will quickly drop to near zero values after lag P. Quickly drop to near zero after values of lag. For example, here is the partial autocorrelation function. This is here is the partial autocorrelation function. For example, the first difference capacity utilization series. The first two, maybe three. First two, consider first two, first leg and the second leg. Two, autocorrelation are statistically significant. This suggests that AR2 or AR3. There is a statistically significant autocorrelation at lag 24, but not printed here. Remember, the 5% of the time we can get an autocorrelation that is more than 2 standard deviation above 0, and in fact true one is 0. But in these two, 1 and 2, there is a statistically significant autocorrelation. Significant autocorrelation. Right? Then the Q measures the moving average component. To get an idea of what order to consider, we examine the to get the what order to consider, so we examine the autocorrelation function. If the time series is moving average of order 1, we call it MA1. We should see only the one significant autocorrelation coefficient at lag 1. This is because MA1 process as a memory of only one period. If the time series is MA2, we should see the only two significant autocorrelation coefficients at lag 1 and lag 2. Generally, for a time series MAQ, the autocorrelation function will have significant correlation up to the lag Q and will quickly drop near zero values after lag Q. Autocorrelation function will have significant correlation up to the lag Q and will quickly drop to near zero values after lag Q. For example, here first lag, it is not near 0, 2 not near 0, after 3 it is zeros. For the capacity utilization time series, autocorrelation functions decays, but only for the first 4 lags. Then it appears to drop off to 0. Autocorrelation function decays. Autocorrelation function. This part is a partial autocorrelation. Only 4 lags. After 4 lags, it decays. Then it appears to drop off to 0 abruptly. Therefore, MA4 might be considered. Then our initial guess is ARIMA autoregressive is 2, and our difference is first difference series, and then our moving average is 4, where the 1 tells the data have been first difference to tender it stationary. Now, in the partial autocorrelation function, D means plus difference, P means the partial autoregressive component, autoregressive AR. How to check this? Partial autocorrelation function will have significant correlation up to the lag P and will quickly drop to near zero values after lag P. Right, after the second or third lag, it falls to the near zero. In this case, generally for the time series moving average, the autocorrelation function have a significant correlation up to the lag Q and will quickly drop to near zero values after lag Q. Right, after the fourth one, it goes to the zero very quickly. Right, now that is, then our ARIMA model is ARIMA 2, AR is 2, plus 1 means plus difference, 4 means moving average. Now let's discuss what is Box-Jenkins method. Here I explain you, using ARIMA to describe the time series, we call it Box-Jenkins methodology. This is Box-Jenkins method. Right? Box-Jenkins methods, besides the smoothing technique, what other methods we can use to forecast univariate data? So then for forecasting, we use smoothing technique. There are any other methods we can use to forecast univariate data. That method is Box-Jenkins method. Box-Jenkins method means capture the past pattern and forecast the future. Capture the past pattern and forecast the future. Why we are using Box-Jenkins method? When facing very complicated data pattern, such as combination of the trend, seasonal, cyclical and random fluctuations, for example, earning data of a corporation, forecasting stock price and forecasting sales, forecasting energy, electricity, gas, forecasting traffic flow of a city, forecasting. Why we are using the Box-Jenkins method? Our purpose is forecasting. The sole purpose is our study is forecasting. Pattern 1. So then here data pattern. complicated data pattern. First, we cannot see any trend. All around cluster around the specific levels that we call no trend, and no trend means just stationary. Then this, with the time, we can see there is a trend. It increased over the time. This graph decreased over time. This graph increased over time in non-linear way. It decreased the values over time. Here trend, right? Here stationary. Here stationary. This is trend. This is seasonality. In the US, electricity consumption, if we consider the electricity consumption, gas, water consumption, right? So then residential consumption, industrial consumption, and commercial consumption. We can see that it's a trend, seasonality. This cyclical. Monthly 3 months treasury bill rate is cyclical. Right, one first prerequisites to apply the Box-Jenkins method is first prerequisite is data series should be stationary. Then Box-Jenkins main idea is any stationary time series can self-predict its own future from the past data. This is self-forecasting. But in practice, we know that not all time series data are stationary. However, it is easy to convert trend or seasonal time series to stationary time series. Simply use the concept differencing. It is when the time t, assume that 2009, index is 89.7. In 2011, it is 90.1. Assume that T3 2012, it is 91.5. 2013, 92.4. 2014, 94.4. Then difference means, what is the difference? Difference between 90.1 and 89.7 is 0.04. Difference between these two values, it is 1.4. Difference between 92.4 and 91.5, it is 0.9. Difference between 94.4 and 92.4, it is 2. This is the differencing. Convert the trend time series to stationary time series using the differencing method. This is the actual data and this is the difference data. If we graph the same data set, same series, in the same graph, this is difference data, this is actual data. Then this is the electricity consumption, it is actual data, this is the difference in data. To convert time series data to stationary time series, to convert seasonal time series, time series, it is D means difference, YT means current year income or GDP in the last year GDP. To convert the seasonal time series to stationary time series, it is current year, and then after the fourth quarter, current first quarter, YT means first quarter, YT minus 4 means fourth quarter. Both of the above two methods can be applied or combined to remove the cyclical effects. Right. Now, how do we decide the model? Which ARIMA model we use? Then, as I explained at the introduction, use autocorrelation and partial autocorrelation function. First order autocorrelation is measure of how correlated an observation is with an observation one period away. This is YT and then YT minus 1. What happened the last year and current year. Second order autocorrelation means, as if that now we are in 2017, it is 20, T minus 1 means 2016, then T minus 2 means 2015. 2 legs. Autoregressive model fit. When the autocorrelation coefficient gradually falls, autocorrelation coefficient and partial autocorrelation, it's gradually diminished to 0, and the partial correlation has spikes. Here, partial autocorrelation has spikes. Then the model depends. Then AR model is appropriate. The order of the model depends on the number of spikes. Here 2 spikes. Then AR2 model is shown below. When the partial autocorrelation coefficient gradually falls to 0 and the autocorrelation has spikes, then MA model is appropriate. The order of the model depends on the number of spikes. Here partial autocorrelation decrease, autocorrelation has spikes. Then we use MA model in the 1 spike. Then we use MA1 model. This one, when both the autocorrelation and partial autocorrelation correlogram shows irregular pattern, then an ARIMA model is appropriate. Irregular patterns, then an ARIMA model is appropriate. Right, whether AR model we use, whether MR model we use, whether if there is an irregular pattern happen, we use ARIMA model. Right, so then what we have discussed as a summary, Box-Jenkins model captures the wide variety of time series data. When faced the complicated time series, it assumes the data set include trend, seasonal factor, cyclical, and random fluctuations. Use the Box-Jenkins is appropriate. This methodology for forecasting is an iterative process that begins by assuming a tentative pattern that is fitted to the data so that error will be minimized. Major assumption of this model: data should be stationary. The difference it could be used to make the data, convert the data to stationary. In using the different models of Box-Jenkins, we depends autocorrelation and partial autocorrelation as diagnostics tools. Computer programs, Minitab, SPSS provide all the analysis tools for use in the Box-Jenkins. Right. Then the ARIMA model, also called Box-Jenkins model, are models that may include autoregressive terms, moving average terms, and difference in operations. Various abbreviations are used. When the model only involves autoregression term, we use it AR model. When the model only improves the moving average, we refer the model MA model. If no differencing involved, abbreviation, the irregular pattern, if we use ARMA model. In most software programs, statistical, the elements in the model are specified in the order. AR order first, AR order, then differencing, then MA order. That's why in our example, AR2, first differencing is 1, and the MA4, 2, 1, 4. The model with 2 AR terms would be specified as ARIMA of order 200. MA2 model, it is 002. Model with 1 AR term and the 1 first difference and the 1 MA term, then we model use 111. Then assume that this is our ARIMA model is 111. Then ZT is xt minus j. And that means first difference we use to account for the linear trend in the data. If order is 2, we use xt minus 1, difference xt minus 1, the second difference. That means first difference of the first difference. This type of difference account for the quadratic and trend in the data. First difference data, it is linear trend in the data. Right, identify the possible model. 3 items should be considered to determine first to guess at an ARIMA model. A time series plot of the data. First time you check the time series plot, then check the autocorrelation function, then check the partial autocorrelation function. There is a possibility of some overall trend, but it might look the way just because there seem to be a big dip in the 15th time or so. So then there is a trend, it's a downturn trend and uptrend, worrying about the trend. Then check the partial autocorrelation and the autocorrelation function. In the autocorrelation function, partial autocorrelation function shows the single spike, partial autocorrelation, single spike at the first leg, and the autocorrelation function showed the tapering pattern. Partial autocorrelation function is a one spike, so then we use AR1 model. Consider the following output. The time series plot of the standardized residuals mostly indicate there is no trend in the residuals. Autocorrelation function, no significant autocorrelation, it is a good result. Normal QQ plot, it is normal probability plot. It also seems good. And the bottom line, young box statistics, the dash blue line is at 0.05. All probability values are above it. Then no significant, non-significant values for these statistics when looking at residuals. Then our overall, the model is good. Consider this autocorrelation and partial autocorrelation data and tried. Suppose that we had misinterpreted the ACF and MP-ACF of the data and had tried an MA1 model rather than AR1 model. The ACF has significant spike. ACF has significant spike at lag 2, and several young box pairs probability values are below that blue line, 0.05. Then the MA1 is not the good model. Right, now this is if your research or if your idea is forecasting for the futures, for example, to forecast the energy consumption, for forecast the GDP growth, for forecast the inflation, for forecasting the share prices. If your idea or if your objective is like that, then partial autocorrelation or the autoregressive or the moving average or the ARIMA model can be used. I upload here, there is a article. See this article. Right, this article is used forecasting real GDP rate through econometric model, an empirical study from Greece. If you want to forecast the real GDP, Then the GDP, we know that it is an important economic indicator for an economic activity and often used by decision makers to plan economic policies. This paper aims objective is modeling and forecasting GDP in Greece. Then they use Box-Jenkins methodology. Considering the data period is 1980 to 2013 with one ARIMA model. Using this model, we forecast the value of real GDP rate 2015, 16 and 17. The statistical results shows the Greece real GDP rate is steadily improving. That is forecast. Right, so then let's see the analysis. This is introduction and this is analysis, Box-Jenkins methodology. It's what the theory we discuss this methodology. If your idea or your purpose is for forecasting the sales. If you are a marketing marketer, you need to forecast the future sales. Then this is the methodology you need to use. Otherwise, your forecasting is wrong. The Box-Jenkins methodology has been used extensively by many researchers in order to highlight the future rates. Right, this is the theoretical background of the Box-Jenkins methodology. The Box-Jenkins ARIMA model is the combination of autoregressive and moving average. AR means autoregressive, MA means moving average. As follows. It is YT. Is beta 0, that is our constant term. YT minus 1, you know that this is Y, dependent variable, and the past value of the dependent variable. And then YT minus up to the P. Right? Then it is the past value of the dependent variable. Also, this is the UT minus 1, UT minus 2, UT minus J. Up to that, it is moving average. The UT means the error term. The Box-Jenkins methodology consists of the following phases. I explain. First, establish the stationary of the time series. The autocorrelation function as well as the augmented Dickey-Fuller test and Philip-Perron test are used to convert the data, to transform the data to stationary process, because the data series GDP is the time series data. The model identification is ARIMA PQ. ARMA is PQ, ARIMA means PIQ. To determine the order of ARMA, P and Q, we use the sample of the autocorrelation function and partial autocorrelation function of the stationary series. These two plots are suggesting the model autocorrelation function and partial autocorrelation function. This is very important. Models we should build. The parameters P is autoregressive operations. Q means the partial autocorrelation Q, moving average. In fact, we use limits plus or minus 2 over square root of n. These are non-significance of the two functions. So we will have a number of ARMA models, A and B. A is greater than 0 and less than P. B is greater than 0, less than Q. For this optimum model, we utilize the criteria of Akaike information criteria or the Schwarz information criteria. Then Box-Jenkins methodology, we estimate the involvement of the white noise term in an ARIMA model. It includes a nonlinear iterative process in the estimation of the parameters, maximum likelihood estimation is used, then diagnostic check-in. And the diagnostic check-in we use, makes our model is statistically significant. Is a Box-Jenkins for the inadequacy of estimate ARIMA model suggested checking the non-random of the residuals. That means whether the residuals from the estimated ARIMA model, whether it has a white noise or not. Then we use for forecasting. One of the main reasons of the analysis of time series model is forecasting. The accuracy of the forecast depends on the forecasting errors. Number of statistical measures are employed for the aim, such as root mean square error, mean absolute errors, mean absolute percentage errors, and inequality coefficient threat. Then the forecast value one period ahead, that means T plus K. We are writing like this. This is the theoretical background of the Box-Jenkins methodology. The empirical results shows that. See the empirical results of this article. Variable used to analyze GDP growth that spanned from 1980 to 2014. The data got from the World Bank. ARIMA approach is used. Then the test in the stationarity. Stationarity check done by using the correlogram of the real GDP in the time series pattern up to the 16 lakhs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 lakhs in levels and for thrust difference. Right, this is levels, this is thrust difference. From the above figures, we can conclude that the coefficients of autocorrelation, this is the autocorrelation column, ACF column, start with high values and decline very slowly, indicating that series are non-stationary. Also the Q statistics or Young box at the 16th leg has a probability value. It is 0.00, which is smaller than 0.05. So then we cannot reject the null hypothesis that real GDP data series are non-stationary. Thus the series must be configured in thrust difference. Right, then this is then the second column. It shows the parallelogram of the real GDP. Then from the figure 2, we conclude that Q statistics and the junk box at the 16th leg has a probability value is greater than, the probability value is 0.214. It is greater than the 0.05. Then we cannot reject the null hypothesis that the GDP series hypothesis, and then we confirm that GDP series are stationary. Then the results of the augmented Dickey-Fuller and Philip-Perrin test are also mentioned here. ADF and the Philip-Perrin test also shows that series are stationary in levels, not levels, first difference. Then identification of the, after testing, then you need to identify the model. Then we can use the parallelogram in figure 1 to determine the model. In the model is ARMA, is ARMA PQ. The value of the parameters P and the Q. As already mentioned above, AR within bracket P moderate the PACF that indicate at leg P, and MAQ has an ACF. In practice, plus or minus 2 over number of square root of sample are the non-significance limits for both functions. To do this, we shall use the automatic model determine criteria AIC and SIC. The limit for both functions are 2 as plus or minus divided by 35 square root. Then the ACF cutoff at lag 2, that is 2.338. Cutoff lag 2, and the PACF at lag 1. PACF at lag 1. Then Q is 2, P is 1. The comparison model within the range exploration using AIC and SIC. Then there is this table, table 2, indicate that according to the criteria, archaic information criterion shows information criteria SIC, the model ARMA is formulated ARMA 1-1. As the model stationary on first difference, then we use ARIMA, that ARIMA 1-1-1. Then this is the model ARIMA 1-1-1. The estimation of the model. Therefore, we proceed for estimation. Next step is estimation. This is the estimate, the model of the ARIMA model, AR1 and the MI1. Then the results in the table 3 indicate that both coefficients are statistically significant because the probability value is less than 5%. Uh, then our model is DGDP is GDP T minus 1, and then GDP ET minus 1 is the function of this. AR1 means lag value. It is error term E value. On the following diagram, the inverse roots MA characteristic polynomial for the stability test presented. Then we can see that ARIMA model is stable since the corresponding inverse roots of the characteristics polynomials all are inside the circle. Then we can use diagnostic check-in for the model. The diagnostic check-in of the model help to check our estimated model are statistically significant. Then we use, for check-in we use Q statistics, Young box, and the normality test for use in Jagpera. Right here we can see the histogram by using the Jagpera. This is the correlogram. The results of figure 4 indicate the residuals. ARIMA model follow the normal distribution. It includes normal distribution. Figure 5 indicate QQ statistics of the Q statistic Young box for all 16 lags, as the probability values are greater than 0.05. Then the null hypothesis can also be rejected. That means there is no autocorrelation for the estimated residuals of the series. Then we use for forecasting ARIMA model for forecasting accuracy test. We do the forecasting accuracy test. Right, this table shows the forecasting test. Now you can see that how the method we discuss is used for forecasting the values. Right, in this paper, this paper is used Box-Jenkins technique for forecasting, and then for that first check the right. Then in our model I explain you how to model the ARIMA model, plot the data for examine the extensionality, then examine the ACF, and then convert the data to the first difference or the logs, and after transforming determine the whether series are stationary or not. Then model identification and estimation, examine the ACF and partial autocorrelation function for determining the ARIMA model. Then estimate the model. Examine the parameter estimates by using SPC, Schwarz information criteria, or the test the white noise. Then use for forecasting. Right, next week by using the practical data set, and let's do the ARIMA model, if you have your own data set, bring your data set for forecasting. If you have the share prices, then you can use the share prices for forecasting. If you have the sales data, if you want to forecast for the future, you can forecast the gather the data and then forecast. If you have the macroeconomic variables or the finance related variables, if you have any idea for forecasting, also gather the data and apply this methodology. It is easier for you to do the assignment or that your research or your project work. If you have that any questions, please keep if you plan to do these subjects for the exam, please submit the assignment, first assignment, and again I am giving you the assignment by using the ARIMA model. Late submissions are not accepted.